Hey guys, I'm Gautam and welcome to IIT Chemistry. So in this video, I am going to talk about the bonding in metal complexes. So till now, we have discussed the corresponding isomers, we have discussed the different kind of ligand, we have discussed how ligand binds to the metal. Okay, I already discussed on how many coordination polyhedrons are possible for a system. Okay, I have discussed everything. Now we are going to a new section over here. That will be very vast section, and that is very important section, that is about bonding in coordination complexes. It will take a lot of time to make you understand, but believe me, from this part you will have at least 3 to 4 questions in your examination, especially in IIT JAM examination. So the first topic that will be on electrostatic theory. Okay, second, EAN rule, effective atomic number rule. These are all the theories present to explain the bonding in metal complexes. What about bonding in metal complexes? There is a ligand, there is a metal. When a ligand binds to the metal, and the bonding procedure how ligand binds to a metal, what are the different process, what are the theories behind it, that in this way this metal will bind to the corresponding metal. So these are the topics, these are the things that we are going to discuss in different theories. So we will be starting from electrostatic theory, then going to effective atomic number rule, then going to VBT, then going to CFT, then going to adjusted CFT, that is called ligand field theory, LFT, and finally we will be talking about MOT, molecular orbital theory. So one by one we will discuss everything. So in today's video, I think we will be discussing only EAN and electrostatic theory, and on the next video forward, so this will take another video, and this will take I think 2 videos, and these 2 will take 2 or 3 videos. So finally we are going to MOT 1 video. Okay, so it will take a lot of time, but once we complete the system, then other part of inorganic chemistry will take very less amount of time. So this part will take maximum amount of time. Okay, so without wasting time, let's get started. So let me talk about first the electrostatic theory. Okay, so we are going to talk about the electrostatic theory. Electrostatic theory. So you know the name, that is electrostatic theory. So electrostatic, you know this word electrostatic, that means the electronic attraction. Okay, attraction or repulsion, some kind of interaction is present. Suppose there is a positive charge and the interaction is occurring in between the positive and negative charge. What we call, this is called attraction. Okay, remember the word interaction. Okay, the word interaction, because this is very basic thing. Interaction means both attraction and repulsion. So if I talk about interaction, that means I am considering both attraction and repulsion. Okay, but if you specify them, that whether it is attraction or whether it is repulsion, that would be far more better. So here I can tell you that here interionic interaction is occurring, and that interaction is our attraction, then it would be far more better. Okay, so now it's okay. So there is in between the positive and negative charge will attract the negative charge, that's why it is attraction. So why this is important? This is important because we know that metal that generally a positive charge species or a electropositive species. Okay, if it is neutral, if the metal is neutral for some complexes, I will be showing you, okay, that in which complexes metal is neutral. So it will be positively charged, or it will be, in general it is also electropositive, so it will love electrons because it is an electrophile. Okay, that will love electron. So it will attract electron from a ligand, and ligand can be, what I told you, ligand can be neutral, but it should have some lone pair, some electron pair to donate. Okay, ligand can be neutral, or ligand can be negatively charged, or ligand sometimes can be positively charged. That is very rare. Okay, but we know NO+, that is ligand is positively charged. Okay, so we don't need to do anything with this. So ligand will have the electron pair to donate. So ligand will donate the electron pair. Why? Because a metal is a electropositive system. So that's how here it is a bonding is forming. Okay, and the name of the bonding is coordinate covalent bond. So the question arises, if I am talking about electrostatic theory, and I told you that this theory is about metal complexes, bonding in metal complexes. So if I talk about electrostatic theory, so a interaction will occur in between the positive and negative charge. Okay, that is called attraction. Okay, yeah, or not only two charges, in between two charges, positive, negative, positive, okay, whatever, in between two charges. So here we are considering electrostatic theory, but we are telling that yeah, this bond is coordinate covalent bond. That means here covalency is present. Here covalency is present. Coordinate plus covalent. Okay, coordinate plus covalent. Okay, now here covalency is present, but in general, whatever electrostatic theory tells, that positive and negative charge just come together and form a electrostatic attraction, and that bond is called ionic bond. That bond is called ionic bond. Okay, so what is the problem over here? So the problem is this theory cannot explain the metal ligand complexes very accurately, or more or less it cannot explain the system for whatever we are going to discuss over here. It is not a successful theory. Okay, so the conclusion is this. So electrostatic theory means electronic interaction between positive and negative charge, but in metal complexes we get the covalency, coordinate covalent bond. So here nothing like ionic bond is forming. Here covalent bond, coordinate covalent bond is forming. Okay, but electrostatic attraction like ionic bonding like Na plus and Cl minus, this is purely ionic. Cl minus, okay, this is Cl minus, this is purely ionic. Electrostatic interaction, electrostatic attraction will be present over here, but in our system there is no electrostatic attraction like that. Here it is covalency. So that means electrostatic theory does have some kind of demerits. Also it does have some kind of merits. So let me talk about those merits and demerits. Those are not that much famous, but let me talk about that. You will get to learn a lot of things. Okay, you will get to learn a lot of things, and I will tell you how this covalency is present in the system. How? Because this is a negative positively charged species. Okay, ligand is a negatively charged anionic species. Okay, I told you ligand can be neutral, anionic or cationic. So take for a moment that ligand is negatively charged. So ligand negatively charged, metal is positively charged. This can be an example. But why I am considering this all time? This is considering like coordinate covalent bond. Why covalence is there? Either whether the ligand is negatively charged or neutral or positively charged, or metal is neutral or positively charged. Why I tell him? Why every time I am telling that it is a covalent bond? Why? Okay, that means whatever we think, if I consider metal as a cation, it's an anion. That means there should be some electrostatic interaction. Okay, but that time also I will be talking about covalency. The bond will be coordinate covalent bond. Why is that? Because in that bond there should be some kind of covalent character. How this covalent character is generating, that I will be talking about this merits and demerits section. So I will be coming one by one. So let me talk about first merit. Okay, I will be talking both at the same time, merits and demerits. So what are the merits and what are the demerits of the electrostatic theory? So the first merit is that electrostatic attraction is applicable for non-transition element. Okay, but it is not applicable for transition element. So how do you explain that it is explained? You can explain this, or give me one example. You can say give me one example so that I can understand that yeah, it cannot explain the things which are present for transition elements. Okay, so to understand that kind of problem, what I need to do, I need to include another term, that is like we call charge density. Okay, charge density, or it is called sometime it is a ionization potential. Okay, ionization potential. So what is charge density? You know the amount of charge, that is Q, and the size of that system. Suppose you have a molecule or you have a atom or ion. These ion have +2 charge. Okay, so you have to take the charge +2, or even this system, if this system has -2 charge, then also you have to take the corresponding mod value so that it becomes positive value, so that charge density can become a positive value. Okay, every time. So you have a system that has +2 charge, that means Q, over that the the value of this charge is Q. Okay, so you have put the 2 value, then you got the radius of the system. Okay, that means size, you got the size of the system. So it will have a charge density. What does that word density means? Density means compactness, the compactness of the system. So if I consider an element, in that element there should be a nucleus, there should be electron cloud, and in that electron cloud what happens? Electrons generally are organizing in a system in such a way so that they can create a cloud. Okay, so now if in a system there is some kind of cloud, so I can tell you that there should be some compactness of electrons. If the nucleus is more powerful, that means the nucleus has more positive charge, okay, then that will attract the electron more and more, so the system will become more compact. If the nucleus is very weak, then it will not attract the electrons, where electron repulsion will predominate, and those electrons cannot form a compact system. So if this electron is forming a compact system, that means that is more dense. As it is more dense, so we can tell that that system will have higher charge density. Done. Another one. Let me talk about another system like opposite one. If there is two systems whose charge is same, but one has larger size, another is smaller size. Which has larger size? Why it has larger size? Because its nucleus is not attracting the system. Whatever the reason is, I don't need to know. If the size is larger, then its nucleus is not attracting its corresponding electrons. Okay, for any reason, I don't need to know that. That means it's not attracting. That means that's why it is large. At the same time, if a system smaller, but the charge on both the system +2 +3 or like that, both of the system is same. Okay. If it is attracting the system, it is smaller. Why it is smaller? Because it is more attracting system, so the charges become, the system becomes more compact. Okay, so for a same charge, size matters. That's why charge density will increase when, if I fix this system, the size, if I fix the size, charge density will increase when the overall charge on the system +2 +3 whatever, okay, that is larger. Okay, done. And if the lower value becomes larger, what will happen? That means two systems that has charge same but size is different. One has bigger size, another has smaller size. Okay, so the smaller size will have the more charge density because charge density is inversely proportional to size. Clear? Okay, done. So I hope I have made you understand. Okay, so now done, it's done. Okay, so sometimes we call the charge density as ionization potential of the system. Okay, so there is nothing like that. So I told you that it is done. Okay, so I was telling you about the merits and demerits of this system, this electrostatic theory. So I told you that for non-transitional elements this theory fits best, but for transitional elements this theory doesn't fit. So why is that? So let me take one example like aluminium 3+ and another two examples, that is Fe3+ and cobalt 3+. So aluminium 3+ is a non-transition element Nt, and these are called transition element Te. Clear? So aluminium, from the experiment it has been seen that in case of aluminium, it has, I am not showing you the charge because all system will have same charge +3 +3 +3, but a system aluminium has smaller size than this. Why? Because aluminium is p block element, these are d block elements, so p block element comes after d block element. Okay, so left to right, if you go left to right the size will decrease, so if decrease, so aluminium 3+ will have lower size, smaller size than this. So aluminium 3+ will be more compact, that means it will have the more charge density than this. As it has the more charge density, then it has positively charged metal, it's a metal positively charged. That means the ligand ligand will be negatively charged, so it will come and attack to the aluminium 3+ and form most stable complex than this, because it has more positive charge density, ligand is negatively charged, more stable bonding formation will occur. But in reality what happens in case of these systems, we get the most stable structure than aluminium. That means electrostatic theory is still only applicable for non-transitional element. It can explain that it will form a complex, but it cannot explain why the transition element, rather its size is higher, then also it is forming more stable structure. In reality it cannot explain. So that's how the merit and demerits of the system works. Second thing is about the ligands. Okay, so in case of in the light of electrostatic theory, what we know that there should be a positive charge on metal, there should be a negative charge on ligand, and this interaction will occur, electrostatic interaction will occur. Now if you have got a ligand, so ligand should have a negative charge according to electrostatic theory, otherwise it will not attract the electron, because there is an attraction between positive and negative charge in case of electrostatic theory. But what if the ligand is neutral, for example NH3, for example H2O, what if the ligand is neutral? Then it doesn't have any kind of negative charge, so why it should not form any kind of bonding, but we know that this kind of complex, we have given examples like that. COH2O6 3+, that means H2 is acting as a ligand in transition metal complexes. Yeah, done. So in these transition metal complexes, as it is a transition metal, so we will call it transition metal complex. So in these transition metal complex, ligand can be, I told you, ligand can be positively charged, negatively charged, even neutral. Even sometimes ligand like NO plus system, this kind of ligand which is positively charged, it can form bond, it can form bond with the metal, because positive should repel themselves, but they don't do it. What they do, they form complexes. That means this theory is not totally successful electrostatic theory. Okay, it only explains about the positive and negative system, not for neutral or positive ligands. Okay, so there is another demerits. The third demerits will be like that. The third example will be like that. That we know that the explain. Okay, we tried with this electrostatic theory, which tells about only the interaction. So this theory cannot explain the color of the system. This theory cannot explain the color. Why the system is showing this color? Why the system is red? Why the copper sulfate is blue? Why like COH2O6 3+ is orange red? Okay, why is that? So the system, this theory cannot explain the color. Okay, even the system cannot explain the magnetic properties. The system cannot explain this, because this system doesn't have that capability to understand the number of unpaired electrons present, because magnetic properties depends upon the number of unpaired electrons, and on that basis, I will be coming on that in the next section, magnetic properties section. On that basis, we can tell you that the system is whether the system is paramagnetic or diamagnetic, but this theory cannot tell that whether the system is diamagnetic or paramagnetic. Okay, because it doesn't have that capability. Done. The fifth example that will explain why we consider there is some kind of covalent character in the complex, and this theory is not able to explain. Why this kind of coordinate covalent bond is forming. Okay, and when this theory only tells about the electricity attraction. So how this is forming, I am telling you. Okay, so listen one thing. Suppose according to this theory, every time what happens? According to this theory, every time metal has a positive charge, okay, and ligand has a negative charge, so that will attract like a ionic manner. Okay, ionic manner. But what if the positive charge, if the charge density CD, becomes too high? Charge density becomes too high. What does that mean? CD equals to what? Charge divided by size, radius. Okay, that means radius will be very low, this term will be predominated. Okay, this time will be predominant. That means charge is very high. If charge is very high, then charge density will be very high. Clear from mathematically? So if a system that has more charge, okay, so according to electrostatic interaction, the more interaction will occur with ligand. But what happens if I am taking, suppose cobalt 3+, okay, cobalt 3+, 3+. So in this system, there is a ligand over here. So ligand has a negative charge, no problem. Ligand has a negative charge, and not only negative charge, ligand also should have some electron density, electron cloud, because every system does have its electron cloud. Okay, so as ligand has the electron cloud, so let me explain this electron cloud like this way. Okay, in this way it has corresponding electron clouds. So when the metal is very powerful, metal has a very high positive charge, then what will happen? This positive charge will attract the electron cloud, of the ligand, and at that time what will happen? This electron cloud will shift like that, in this way. Okay, and this electron cloud will be like this, and when this electron cloud shifting is occurring, this factor is called, the factor is called, let me write over here, polarization of what? Polarization of the ligand electron cloud. If this kind of polarization is occurring, that means overlapping between the metal and ligand is occurring, and here the covalency generates. This is the reason why covalency generates. So remember, every time when in a system some kind of polarization is occurring, that means in that system covalency is creating. Okay, the system is creating some kind of covalent character. Okay, so that's the reason why covalent character is there, and we are calling it the coordinate covalent bond. Okay, I think it's clear. Done. So now let me talk about this. I have told you everything about the electrostatic theory. There is nothing else with this electrostatic theory. I told merit, demerit, covalent character, why is that, everything I told you. So now we don't want to, we are going to get the second structure, second theory, that is about our electron effective atomic number rule. So let me write that one. We are going to discuss the EAN, that means effective atomic number, effective atomic number rule. That is called, in shortcut it is called EAN rule. So remember this one, this is very important rule. And these rules, sometimes these rules becomes, sometimes, what focus on that word, sometimes. Okay, let me write this. Sometimes this rule is also called 18 electron rule. Why, what will be that time, I will be talking about that 18 electron rule. So these both rule are not same, but sometimes EAN will be considered as 18 electron rule. Okay, so just tell me one thing, are you stable? Just tell me one thing, are you stable? You will say, what is the meaning of this question? The meaning of this question is, I am asking you, are you stable? And the answer of this question is yes, you are stable, and that's why you are watching my video, that's why you are sitting in your home, and that's why you are doing your job, because you feel comfortable and you are okay with that. That means you are stable. So every system wants to be stable. Okay, and to be stable, the system should have some properties. And if I say the system should have some particular number of electrons, because there is a universe, in this universe there should be some rules, okay, the rules and regulations. So this system should have, metal complexes should have some kind of limitations or some kind of restrictions, and that restriction is called, I can say here for this system, here I can say effective atomic number or 18 electron rule. Okay, so especially if I tell you the 18 electron rule will be that corresponding limitation or that corresponding restriction in which the system could be stable. Okay, that means 18 electrons. So we are doing business here, we are doing business with numbers, and what is that number? The number is 18. So there is something that 18 electron system is stable. So there is nothing like that. Okay, so 18 electron rule means that is coming from EAN. So you can ask, why 18 electron, why 18? So that I will make you understand from EAN. So you know that in the periodic table, helium, neon, argon, then what comes? 36, krypton, 54, xenon, and finally take till now, okay, radon. These are very stable complexes, very stable, because these are what? Noble element or noble gas, noble elements, and these are stable. So if a system gets these number of electrons, then if this system can be stable, this noble gas can be stable, then the system which will get these number of electrons, total these number of electrons should be stable. Logically that should be correct. Or yes, here is the concept comes EAN, effective atomic number. From here the concept is coming, effective atomic number. So the system which will have this amount of electrons in total, this system should be sometimes this system should be very, very stable. And if the system should have this amount of electrons, then the system will follow 18 electron rule. How I am getting into that? So listen, we have nothing to do with this system. We have nothing to do that, because till argon there is no transition metal elements. After argon, that is from 21, okay, 21 scandium, titanium, vanadium. Okay, from a scandium transition metal complex metal elements are starting. So we have nothing to do with this. Okay, so ignore this. We will start from krypton. Okay, and verify whether the system is carrying this amount of electrons or not. So let me take one example for that. Okay, let me take one example for that. So suppose I am taking a general example. For example, metal and Ml6. Okay, and I have nothing to do with this part. I will do business with this part only. So in this part there is a metal. This has some kind of charge. I don't know what is that. There is a ligand that has donating electron pair, right? So I will discuss two factors. First, EAN, second, 18 electron rule. So how these are same, how these are different? EAN is a much broader term. 18 electron rule is a smaller term, okay, and that comes in that EAN rule, okay. So let me make you understand that. So in the EAN rule, what you need to do, you just need to get the total number of electrons of this metal have in the complex. Okay, so in this complex, the total number of electron present on this metal, so metal electron plus the number of donating electron by ligand. So carefully look at carefully. The number of electrons present in a metal plus total number of electron, the number of electrons that metal contains. So the total number of electrons present in that metal is, and add that with the value of number of donating electrons by the ligand. So don't add, if the ligand has 100 electrons, don't add 100. To add the numbers, add the number of electrons which are donating by the ligand. Okay. So if the ligand donates 5 electrons, add 5 to the metal. If the ligand donates 10 electron, add 10 to the metal electron. Okay, so metal, you have to consider the whole number of total number of electrons present in the metal, but you don't need to consider total number of electrons present in the ligand. You just need to consider the ligands which are the ligands donating the number of, suppose the ligand is donating 5 or 10 electrons. So you just have to consider these 10 electrons. Why is that? Because metal is fixed, metal is here, and from other sides ligands are coming. So as ligands are coming, so every ligand will donate a certain amount of electrons. So you just have to consider that. Okay, you have to just do business with the metal's ligands electron, the number of electrons which are donating. Okay, the ligands are donating. So you just have to consider that number of electrons, not whole number of electrons from the ligand. Done. Okay, so another factor is 18 electron rule. So what is the basic differences? So the term 18 is coming not from here, from here you are not getting 18 watt, right? So here it was 18, but it has nothing to do with this. So why the watt is coming 18? So let me make you understand that first. Then I am telling you why 18 electron rule, what is 18 electron rule and how it is related to EAN. So you know that in case of take any element, any transition metal element, TME, and in that case it has the valence electron. Do you know about valence electron? 3d, sorry, 4s and 4p. So you know that for a transition metal element, it has the corresponding valence electron 3d, 4s and 4p. These are the valence electrons. So if I talk about electronic configuration like Fe2 plus, so what is that? The configuration is 3d6, 4s2, and there is no electron in 4p. That means 4p0. But the orbital is present. 4p orbital is present in the system. So here 1, 2, 3, 4, 5 orbitals, 5 rooms, 1, 2, 3, 4, 6 rooms, 7 room, 8 room, 9 room. Okay, 5 and 4, 9 room. So in each room, how many electrons should present? 2, 2, 2, 2 and 2. So here it is 10 electrons present, can present maximum number of electrons I am talking about. From here to here 6. So add that value 10 to 6, that you will get 18. That means in case of EAN, we are considering the total number of electrons, we are considering all the orbitals. But in case of 18 electron rule, from here we get the idea that we have to consider only valence orbital of metal. We need to consider only valence metal electron plus same donating number of ligands, donating electrons by ligand. So this is same in both the cases, but here is the difference. Here total number of electrons, here only the valence electron you will have to consider, and the valence electron is what? 3d, 4s, 4p in first transition series. So in general what will be? That will be like n-1d, ns and np. So second transition series it will be 4d, 5s, 5p, third 5d, 6s, 6p, like that. Okay, so these we have to consider these orbitals and the number of electrons present in these orbitals to get the 18 electron rule, to satisfy the 18 electron rule. Okay, another important layer here is, if the system has, I told you that to make the system stable, this amount of electrons should be present. then we can say that as these are stable with this amount of electrons, so any complex will be stable with this amount of electron. So here if the system has the EAN, I will make all the calculations, just wait. If the system has EAN 36 or EAN 54 or EAN 72, then we will say that the system is obeying 8. Now every time we will say that this is a value, effective atomic number, so it's a number only. But if this number is specific like 36, 54 or 72, I mean this value, okay, then this value, if the EAN contains these values, then we will see that corresponding metal complex will follow the 18 electron rule. Why is that? Because if you consider this, all these are if you multiply 18 with something integer, okay, then you will get 36, 18 into 2, 36, 3, 54, 4, 72, okay. And is that what that I told you? No. If you count the total number of electron with this formula, number of valence electron plus number of electrons donated by the ligand, then also you will get 18 for if the EN value is this. So for EN value this and this, 18 electron rule will also be satisfied. If the EN value is not this, then if you count the number of electrons from valence and this, you will not get the total number of electrons. That means the system will not obey the 18 electron rule. I think it's clear. Right? Okay, done, no problem. So now let me give you some example. For that. Okay, let me give you some example for that. First example, let me take one example like COCN whole 6, okay, and here it is charge 3 minus. So I told you I will just calculate the EAN. So how to calculate EAN? To calculate EAN, effective atomic number, I have to consider the total number of electrons present in the metal, on the metal. So here there is some kind of charges like that. So how to count? Three charge means 3 electron, a lot of things. So make it simple. I am using here oxidation state method. So what is this method? There is another method that is named neutral atom method. So I am not talking about this right now. I will be talking about both of these methods again in the organometallic chemistry. But here we will be only talking about oxidation state method. So here you know what is oxidation state method. You can see that there should be an oxidation state present in the system. We have to consider the oxidation state of the system. So whose oxidation state? Metal's oxidation state, ligand oxidation state. Okay, and how to calculate that? Let me show you. Here is a metal present in the system. Okay, I am calculating EAN, total number of electrons present on the system and number of electrons donating by the ligand. So here cobalt, that means cobalt will have how many electrons? Cobalt will have CO. So I don't know how many electrons are present on the cobalt because I have to calculate the oxidation state of cobalt, metal and ligand both. So I know cobalt, that means X, I don't know its oxidation state. So there the ligand is connected is like CN. So you know about CN. If you don't know the oxidation state of CN, do one thing. Take a complex of CN, like I am taking HCN. Break it, ionize it. What I get? H plus, CN minus. So that means CN has generally 1 minus. So you know about that. The CN is not CN. CN is actually CN minus that acts as a ligand. So CN is CN minus. So how many CN minus are there? 6. So for 1 CN minus, what is the charge? Minus 1. Okay. For 6 CN minus, 6 into minus 1, and overall charge is what? Minus 3 equals to minus 3. X will be plus 3. That means the corresponding metal CO is present in the system as CO3 plus because X has values plus 3, and this plus 3 is the oxidation state. Okay, is a oxidation state, not the charge on the metal. It's the oxidation state. Okay, this is the oxidation state. So it's done. So cobalt, I know the cobalt oxidation state. I am just doing it for one system. Otherwise, you can do for other system also. So cobalt, that means argon. After argon, it is 3D something like 7. 3D7, 4s2, 4p0. But for cobalt 2 plus, what will be? 3d6, 4s0, 4p0. So 3d6. Okay, but in case of EN, I have to consider all the electrons. So I cannot consider 3d6. So 3d6 for this system. But as cobalt, he has total 27 electrons in at present. If I lose 3 electron, how many electron will be there? It will be total 24 electron from cobalt, right? Okay, done. And for one ligand CN, according to oxidation state method, I told you I will be teaching you about oxidation state method, but in most of the cases, every ligand according to oxidation state method, every ligand donates at least 2 electron. Whatever example I will be giving over here, okay? But I will be talking about oxidation state method and neutral atom method later on in the organometallic chemistry. So don't worry, I will be teaching that one. So Cn is donating 2 electron. So one Cn is donating 2 electron, 6 Cn will donate 2 into 6. That means total 12 plus 24, 36. What is that? Krypton. What is that? Krypton. And what about krypton? Noble configuration. You know that. So as it is forming a noble configuration, so it is stable. So I told you that if the system has EAN 36, 54 or 72, that means then this will follow the 18 electron rule. How is this? So for 18 electron rule, we just need to consider the valence electron. So do that. Let's do that. Okay, so I am doing over here. So it will take small places. Okay, small amount of place. So cobalt 3 plus, I know the oxidation state of cobalt. That means cobalt does have how many electrons? If consider this system, consider this part. I don't need to consider all the electrons. I just need to consider the valence electrons, and the valence orbitals are this. So the number of electrons present in these orbitals will be valence. So this is cobalt 3 plus. So cobalt 3 plus has only 6 electrons, right? 6 plus ligand is donating 2 into 6, 12 plus 6, 18. So you got 18. Okay, so you got 18. That means cobalt 3 plus is following 18 electron rule. Clear? I think it's clear totally. Another system. Let me take another system, number 2. So I will be taking CrCO whole 6. Here listen, CO. What is that? It's a neutral ligand. Neutral ligand. Okay, neutral ligand. And this neutral ligand has what charge? 0. So overall system has charge 0. So metal has charge what? 0. Okay, if you calculate x plus 0 equals to 0, that is x will be 0. So I don't need to calculate that. So chromium's total number of electron will be 3d 5 4s1 and 4s0 4p0. That means total chromium has electron 24. You know that. Okay, you know that. And carbonyl CO 6 carbonyl 2 into 6 equals to what? 12. Summation 36. Krypton again. Okay, so let me calculate the valence. Valence means here it is 5 plus 1 6 plus 6 into 12. 6 into 2 12, 18 electron rule. So it has EAN 36. It follows the 18 electron rule. So it has been proved that if a system has this amount of electrons in the valence shell, totally this amount of electrons, it will follow the corresponding 18 electron rule. If the system doesn't have that amount of electron, so then the system will not obey the same. Okay, so let me take you another example. So that is little bit different. Okay, so I am giving you the 3 different examples, then I will be giving you some homework. Okay, so you need to do that in this session also. Okay, whenever you are watching that video. CO whole thrice and finally NO, and the whole system has charge plus. Okay, okay, no, there is no charge on the system. So first you need to calculate the oxidation state of metal. So you know it has charge 0, but here it is NO. According to oxidation state method, because we are following this oxidation state method, so according to oxidation state method, this has charge plus 1. That is NO is not NO. NO is equals to NO plus. Clear? So here it is X, here it is 0, here it is plus 1. Okay, and that overall charge is 0. X will be minus 1. So I told you this is the oxidation state. This is not the actual charge on the metal. Okay, so metal is negatively charged. Don't think like that. Okay, but here you can think about that. It has oxidation state minus 1. So there will be total number of electron plus 1 electron for this minus 1, because minus 1 means 1 electron extra. So cobalt minus 1 will have how many electrons? In general it has 27 electron plus 1, 28 electron. It will have 3 CO. How many electrons? 6 electrons. Okay, no problem. 1 NO. How many electrons? It has 2 electron, of course. So 6 to 28, how many? 36 electron. That is also true. That is also for krypton. Okay, is it interesting, right? So this is also for krypton. That means it will follow 18 electron rule also. Should I do this? Yeah, let me do this. Cobalt, okay, no problem. Cobalt -1, 3d7, 4s2, 4p0, plus 1 electron for 1 negative charge. That means 7 plus 2 plus 1, 10 electron from cobalt -1. 3co6, 1 no, 2, 6 plus 2, 8 plus 8 equals to 18. So now we have got what I am telling about. Okay, so let me provide you some kind of homework. Okay, let me give you some kind of homework, okay, so that you can check that. Okay, so do one thing, do the work like this. Fe, so do now. Okay, whenever you are watching this video, do now please, and do one thing. After solving this, send it in the group. Okay, I will be checking that one. Really, I will be checking that one. FeCN whole 6 4 minus. Okay, FeCN whole 6 4 minus. Okay, no problem. Yeah, so do this for this, do this for PtCl2 NH3 whole 4, do this for, okay, this is platinum, so consider another thing, but do check both the EAN and 18 electron rule, do check all these two. Okay. Then let me give you another example. Okay, let me give you another example like Mn CH3 and CO whole 5. So let me tell you, this is CH3 like what is CH3? Here CH3 is actually CH3 minus, and how it forms, let me show you. This is very important to show. No one shows this kind of things. Okay, so here suppose someone takes this H plus out. So when someone takes this H plus out, then this kind of bond break, this in this way the bond will break, and when this bond is breaking, the carbon, it has 1 electron, hydrogen has 1 electron. So carbon has its own electron right now also, and it has also got this electron. Okay, so what will be the product? The product will be C. These 3 hydrogen will be the same as in the previous one. This is carbon's electron and this is hydrogen electron. So as this electron is coming to carbon, so this is why there is a negative charge. Okay, so as 1 electron is coming to carbon, this is why this negative charge. Don't consider this that these 2 electron is coming, because the present electron, the previous electron was present on the carbon, and now it is also carbon. Just it was participating in the bonding. Okay, so that's why this negative charge is for this electron, this extra electron. So this system, we don't write this negative charge. We write the negative charge for this system, but for our simplicity, what we do, we just write without writing these 2 negative charge, we just write a negative charge, and we consider that this negative charge means 2 electrons. This is 2 because it in this position there are 2 electrons. Okay, nothing like that. So that is what the system has 2 electrons over here. Okay, that's how it donates 2 electron. So it will donate how many electron? 2 electron. It will donate 5 into 2, 10 electron. Okay, but before we do, we need to calculate the oxidation state. Metal, I don't know, X, overall 0, CH3, that is actually CH3 minus 1 plus 0. Okay, so X will be plus 1, X will be plus 1. Okay, X will be plus 1, that means manganese plus, that means 3d 5 4s1 4p0, and manganese has total how many electrons? 25 electrons. So as it is manganese plus, so 24 electrons plus 2 electron plus 10 electron, 12 electron total, 24 plus 12, that means 36. Krypton, this is the EAN, effective atomic number is 36 for the system. And if I talk about the 18 electron rule, what will happen? Okay, let me do that. Okay, what I did, okay, let me do that over here. So it has how many electrons? 5 plus 1, 6 electrons plus 12 electrons from the ligands. Do summation, you will get 18 electron. So that's how we are getting 18 electron for this case also. Okay, so that's all about these things. Now let me talk about some other examples like yeah, so let me provide you some homework. Okay, let me provide you some homework. That will help you a lot. Another homework I am giving you, that BCO whole 6. I will be solving all this homework in my organometallic compound, so don't think that I am ignoring this question. No, I am just giving you for practice. Okay, I will be giving you some assignments also. Whatever, if you are regularly following me, then it's okay, it's very good for you. Okay, see every day's video every day, so that will be very good for you. Okay, done. So I have given you 3 examples, so do that. Okay, and I will be showing you something new, because I don't want to show you a lot of things like that and waste my time. So I will be showing you another thing, like I'm taking another example. This is very interesting. Okay, CrCO whole thrice eta 6 C6H6. Okay, so I think that would be far more better. Okay, so what about C6H6? Do you know C6H6 it is what? This is a benzene. Right? So in this system, eta 6, what does that mean? Eta means eta 6, that denotes the hapticity. What is hapticity? What about hapticity? Eta 6 means the system is donating from 6 sites. And how many electrons will be donating? That will be depending upon the corresponding method, which method you are using. For oxidation state method, the rule will be different. For neutral atom method, the rule will be different. But for neutral ligands, that means it is a neutral ligand. But for neutral ligands, both oxidation state method and neutral atom method will provide the same number of electrons. Okay, but here it is a neutral ligand, so there is nothing to do. And the difference between these and if for charged system, how oxidation state method and neutral atom method works, I told you that I will be telling that in the organometallic chemistry section when I will be discussing, I will be comparing these two. Okay, but now whether whatever things are necessary, I will be telling. So as this is a full neutral system, so it is for both the cases it will be donating the same number of electrons. Okay, so it donates 6 electrons. How 6 electrons? Look at the system. How many pi electrons are there in system? 1, 2, 3, 4, 5, 6. And I told you pi electrons are very weak. You know that pi electrons are very weak, and as pi electrons are very weak, they can donate to this system, donate to this metal from these and these 6 different sites. So how do I represent this? So you can represent this by this way. Let me draw the structure again. Cr, this is CO, this is CO, this is CO. Okay, let me write this CO because it is connected to carbon. Okay, CO. And this 6 is attracting like this. So you know the resonating structure. We write the resonating structure of benzene like this, because these 3 bonds are delocalizing over the system, right? So that's why you can write the system, you can draw the system like this. And this 1, 2, 3, 4, 5, 6 atoms are donating simultaneously. So that's why I just did the whole system like a round structure. Okay, so that's why 6, 1, 2, 3, 4, 5, 6 donating, and that's why it is called that's why it is eta 6 ligand. Okay, eta 6 benzene, and formula is C6H6. Done. So how many electrons is there in this? How many electrons are there? Listen. First, let me find out the oxidation state, that is neutral. Okay, because the ligand is also neutral, overall charge is neutral, CO carbon is also neutral. So as this is neutral, so how many? Chromium 0, that means D4, 3D4, sorry 3D5, exception it is 4S1, 4P0. So if I talk about EAN, then chromium, that is 24 electron. How many electron? 2, 6 plus. Here eta 6 means as it is a neutral ligand, how many electron is it is donating? 1, 2, 3, 4, 5, 6 pi electrons are there. So 6 electron it is donating, 6. 24 plus 6 plus 6, 36, krypton again. So it should follow 18 electron rule. How? Let me discuss. So D5, that means do it, just pause the video and do it yourself. That will be quite fun. Okay, so 5 plus 1, 6 plus 6 plus 6 from ligand, 18. Clear? I hope it's totally cleared. Now another question is coming over here. If the system is, I told you that it is neutral. I told you that it is neutral. So for neutral system, whatever method you are choosing, oxidation state, neutral atom, I didn't teach the neutral atom method, just let me tell, just okay, nothing else. Whatever method you are choosing, that will give the same number of electrons to donate to the metal. But if I take another system where this is charged like that, and in that system if I take the oxidation state method, I don't talk about neutral atom method, I don't want to discuss that. Okay, I will take oxidation state method. So if I take that one, if I use oxidation state method for that, for the charge system, what will be the number of electron that it will donate? Okay, so it is donating from 6 different sides and number of electron is 6, that's why it is eta 6. So let me take another example like that. So I am taking a example like charge system and I am donating the corresponding electron. Okay, so what, let's see what happens. So the system is like that, Cr CO whole thrice eta 5 C5 H5. So let me talk about this C5 H5 system. This is a system like this, cyclopentadiene, and here it has 2 hydrogen. So it has 1 2 3 4 5 carbon, 1 2 3 4 5 6 hydrogen. So to make eta 5 C5, I need to eat 1 H. So how to do that? Just put a base and take this H. It will abstract this base and here will be a negative charge. Negative charge, hydrogen like that, and these negative charge is delocalizing in the system. Okay, here negative and here, then it will come over here and here, and this here and here, and a negative charge here, again resonance here. Let me draw the structure like this, and here and here. So you can draw other structures. So that why I am drawing this, because these, whenever these negative charge is forming, because it is C5 H5, okay, so that's why it should lose this hydrogen. Okay, after losing this hydrogen there is a negative charge forming in the system, and these negative charge is delocalizing, and if you know the aromaticity, then you can say that this system is aromatic because of this negative charge. Okay, otherwise wait for my organic chemistry video. So this system is totally done. Okay, I am done with this system. So as this system is totally cleared for you guys, that's why this negative charge is delocalizing over the system. So that means 1 2 3 4 5 carbon is there. From 5 carbon you can donate the system. So if you draw the system in such way, Cr CO CO and CO, and here 1 2 3 4 5 membering, 1 round, and here it is done. So here the ligand, you can see that this is a C5H5, but it is not neutral. It is what? It is a charged -1 system. Okay, it is charged system. So how many electron it is donating? Okay, so from 5 system, 1 2 3 4 5 atom it is donating. So that's why it is eta 5. Hapticity is 5. It is connected to, this bond is connected to 5 atom. Okay, so from here, from everywhere it is donating, and which it is donating? It is donating the pi electrons. These negative charge will be considered as a pi electron. So this pi electron, and negative charge means what? I told you, negative charge comes for 1 electron, but it denotes the 2 electrons. Okay, so 2 electron, 6 electron is there. So it will donate total 6 electron. Okay, it will donate total 6 electrons. So chromium, it is a D4, that means it has total 24 electrons. Here 3 into 2 6 electron, here 6 electron, 36 krypton. Clear? It's quite interesting, right? So that's why, so it is called hapticity is what? Hapticity is what? 5. That's why it is eta 5 C5 H5, and it has a special name. When we will learn ferrocene, it has a special name like eta 5 CP. CP means what? Cyclopentadienyl anion. This is called cyclopentadienyl anion. Okay, so it's done totally. Okay, no problem. So I think I have shown you a lot of examples for you. Okay, so I will be teaching you again these things in the organometallic chemistry section. So don't worry, you will learn everything. Okay guys, So done. So yeah, so let me give you some other examples. Okay, so check this system also. Other examples means homework, of course. FeCO whole 5, then NiCO whole 4, then CO2. This CO is metal, this is carbonyl. CO whole twice, eta 5 Cp. What is Cp? I have shown you. Okay, so just do calculate both EAN and 18 electron rule. Does it satisfying? Does it satisfy or not? And send it in the group. Strictly telling, send this in the group. Okay. Then do one thing, calculate this for FeCO whole 4 2 minus. Then do calculate for FeCO whole 2. Sorry, I did the mistake. Okay, FeCO whole 2 NO 2. Okay. Then do it for CO whole thrice. You know why I am giving you all these examples, because you will face some questions in the examination. Okay, and they will ask you which of the system is following 18 electron rule. So I have already taught you that how to find the total number of electrons through oxidation state method. Okay, I just need to teach you only one, but at that time I will be comparing both of these and teach you both of those. Okay, but you have already learned about the oxidation state method. Okay, so that's amazing. Fine, so you can do all these things, all these stuffs, and do this. So now I need to come to another question, that is, what is the application of 18 electron rule? What is the application of this EAN, or that means or 18 electron rule application, or of EAN? What is the application? So let me talk about the first application. The first application is that EAN, or directly EAN or indirectly 18 electron rule. Okay, so I told you that if the system does have a EAN like 36, 54, 72. Okay, so if the system has EAN value, this will follow the 18 electron rule, and if the system follows 18 electron rule, remember the system is stable. Okay, I told you already. So I am giving one example, CO whole 4. So this is cobalt, this is carbonyl. So if we calculate, its EAN value will be 35, and so it is not stable that much. Okay, so to make this stable, actually this system doesn't exist. Okay, because it feels I am not stable. I told you, are you stable? This system is telling the answer, no, I am not stable. So that's why I am making a dimer, CO2 CO whole 8. So as it is making a dimer, it can follow now 18 electron rule, or the effective atomic number from this or this. Okay, so let me show you that one also. I won't neglect this, I won't ignore this. Cobalt, there is 2 cobalt, 1 cobalt, and the whole system is overall charge 0, and metal is, here it is CO ligand, that means metal is in 0 oxidation state. 2 cobalt, 1 cobalt 27 electron, it has 2 cobalt 27 into 2 54 electron. Then 8 CO, 8 into 2, that means 16 electron. How many? 70, not 72 yaar. So it's 70. I missed something. What I missed? Let me draw the actual structure of cobalt. CO I have given. Okay, and I missed one thing. What? This bond, right? CO bond. Because otherwise, how to show you that these two systems is forming dimer? There should be a cobalt metal bond, and this bond has 2 electrons. 72. That means this. That means it follows. If you calculate this, it follows 18 electron rule. How to calculate for the system that it follows the 18 electron rule? You can do that, or I will do it in the organometallic section. I don't need to explain anymore. Okay, you can do that. How to do that? Take this system as a reference. Take this part only. So you take 1, 1, 2, 1, 2, 1, 2 like that, and you take cobalt. 27 on 28, 28 plus 1 2 3 4, 28 plus 4 means 8, 28 plus 8, that is 36. Okay, so for the system, if you take the valence electron only, you will get 18, no problem. Okay, so or you can do one thing. Why this system is, I told you why this system is following 18 electron rule, because it is, if you take 18 and multiply 2 3 4, if you are going with this, then you will get with 2 36, with 3 54, 4 72. That means this is a multiple of 18. That's why you are getting that these are following 18 electron rule. Okay, so nothing else. Okay, so this is one application. Another application, what can I get, what can I explain? Another application is that in a system, okay, in a system, like there is CO whole 6. I am taking this system. So if you calculate the total number of electron in the system, that is 17. Total number of valence electron, okay, that is 17. Okay, I am taking only not EAN, just 18 electron. If I am checking whether it is following 18 electron rule or not, do it, just check the EAN value, of course. So it has not 18 electron rule, it has 17 electron rule. I told you that 17 electron system are not that much stable, so I need to be stable. So I will accept one electron and be stable. It will accept one electron. I will explain this in the organometallic section, why is and how the reaction occurs, how can this system take one electron. Okay, I will tell that in the, but here it's not necessary. I am reading, we are teaching here, we are learning the metal complexes, the bonding, so we don't need that. BCO whole 6, and overall it should have minus charge, so it will have 18 electron rule. Just do check yourself, do not think that yeah I am right, so sir is right, so I am not checking. Do check yourself. So it is another application. There is third application. From 18 electron rule, I told you from 18 electron rule or EAN, I told you most of the complex will follow 18 electron rule to be stable. So I consider that a system is stable, that means it should follow 18 electron rule, but I don't know the structure of the complex. So there is a system like eta 5 CP, you know about this, right? Okay, Fe, that is connected to Fe, one CO is connected, and one C7H7 ring. How does it look like? This and this. Here is only negative charge. This system is not also neutral, so it will be eta 7. Okay, it will be eta 7. So let me, I am not calculating the EAN, I am calculating whether it is satisfying the corresponding 18 electron rule or not. You can calculate the EAN also. So here Fe is X, Fe has oxidation state X, I don't know, Cp minus 1, CO 0, this has minus 1, equals to overall charge 0, X equals to plus 2, iron plus 2. Okay, let me write that, iron 2 plus. That means how many electrons it will have? It has electronic configuration 3d6, 4s0 and 4p. Okay, 4p0, so 6 electron over here, 6 plus eta 5 Cp, that donates 6 electrons. I told you why, because of this negative charge. Okay, according to oxidation state method, plus from carbonyl it will be 2, plus from here it will donate 7, and for this negative 8 electron. How many electron will be there? How many electron will be there? There will be total 6, 6, 12, 14 and 8, 22. Not stable. The system is not stable. So for that is what I am going to explain, that you can get the exact structure of the system. Okay, that this system will not donate it 7 electron. This system will donate only this part. All this part will be inert. Okay, this part left of this part will be inert. This part will not participate into resonance. This part will not participate into this hapticity. Okay, so if it will not occur like this, so what will happen? Only this part will be like that. Okay, let me write this one. Okay, so these negative charge will come. Okay, sorry, these negative charge will come over here, these negative charge will come over here, and this bond will break. Here it will be double bond, negative charge, and here it will double bonds. Again these negative charge will come here, it will be like there. So the delocalization I will consider only in this part. Okay, only in this part, only in this part, only let me use the color, only in this part, only in this part. Okay, only in this part, not in the section, not in this section. Okay, not in this section, only in this part. So that's why as the delocalization is occurring only in this part, 1 carbon, 2 carbon, 3 carbon, there is 3 carbon, so it will donate eta 3, not eta 7, not eta 7. Okay, clear? So it will be eta 3 and the formula will be same, C7H7. Okay, so as it is eta 3, now listen one thing, eta 3 means there is one negative charge, that means total electron donation will be 4. So here put 4, here in place of 8 put 4, 6 plus 6 12, 16, 12, 14, 18. Now it is following 18 electron rule. So what we have learned over here, that from 18 electron rule we can get the hapticity, that I don't know how many electron it will donate. So to get 18 it should donate 4 electron. That means in a system it will be like that eta 3 hapticity. That means it will be donating the system to only from this section. If I draw this section, over here, what we get? If I draw this eta 3 C7 H7 system, how do I draw this? This part. I will be considering only this part for bonding. Other part will be intact. Okay, this and this will be intact. Okay, this part will take part in the bonding. Okay, so that's how we can get how many electrons it will donate and how the hapticity will work. In this case, eta 3, that will be eta 3, eta 4, eta 8, eta 7, whatever. That I can discuss, I can get from the 18 electron rule, because 18 electron rule, every system wants that he should get some 18 electron, or he should get the one number from EAN that is stable. But that doesn't mean that for every case, for every system follows this 18 electron rule or try to follow the 18 electron rule. But in most of the cases, system try to follow the 18 electron rule. So in most of the cases, you can apply this theory. Even if you face questions in examination, you will think that the system will face, that the system will show 18 electron rule. The system will follow the 18 electron rule. That is how you can get the eta 3, that will be eta 3, eta 4 or eta n, whatever you can calculate from this, by applying the 18 electron rule. Clear now? Okay, done. Okay, done, no problem. Done. So that is what 18 electron rule is. Now let me talk about some limitation of this rule. Okay, some kind of limitation. Let me talk about some limitation. So you know that you knew about this structure, C7H7 like that, you knew the structure. Okay, and you can draw this system, you can explain the system very perfectly as it is following the 18 electron rule, and it's the real structure. But from this structure, can you explain that from EAN rule, can you explain that what will be the geometry of this complex? Tell me, what will be the geometry of this complex? No. Even the structural information is available for this EAN for this system? No. I don't know the exact structural information. Again, if I talk about something like, I take one system, one metal, okay, one system, like one thing, how this system cannot explain the structural information. I am taking one example, a big example, Fe3CO12. Okay, I will not do the calculation. If you are interested, do that and send me in the group. Okay, so I am taking this system, and this system especially follow 18 electron rule, or this system follow 18 electron rule per metal. Okay, if you consider one metal, that will follow 18, another metal 18, another metal 18. For whole system you will get some multiple of 18. Okay, you know that. I know that this is following that, but the structure of the system, if I draw like this, I do have two possibilities like this, Fe, Fe and Fe. So if I attach like this, and 1 2 3 4, 1 2 3 4, 1 2 3 4, so 4 4 here, 4 4 4, 12, no problem, 12 CO is attached here everywhere, I am not writing. 3 is Fe connected this bond, so 3 like that single bond. So if I draw this, I will get total number of electron in this system is 18. Okay, that means it is following 18 electron rule. Up I calculate this. I will calculate for this system also in organometallic chemistry. Okay, so I will do that. But this theory, EAN theory, cannot explain that if there is something like bridging ligand. You know about bridging ligand, the ligand who is form a bridge between two ligand. I told you, here is a metal, here is a metal. If in between these two metal, or with these two metal is connected through a bridging ligand, that means here it is take as CO. Okay, take it CO, two metal, and here is CO. The metal is not connected from here to here. Okay, like this way. This is the connection of the metal. Okay, this is the connection of the metal directly. This is the connection of the metal directly. But in this whatever case I am talking about, this is not there. Okay, only here it is coming, here it is CO, and finally here it is CO. That means two metal, and in between them CO is present. CO is connected to this and CO is connected to this, and that's how these two are connected like a bridge. In between there is a river, and here one village, another village, and the bridge is connecting that two villages, and that bridge is CO. So in that case, if I draw the system in that case, then also it will follow the 18 electron rule. So in both cases, if the system is following 18 electron rule, so I cannot explain the structure, that whether in the system there is a bridge or not, or there is a metal bond, or metal bridge, metal carbonyl metal bond. Okay, so I cannot confirm from the EAN rule. So this is some kind of problem with EAN rule, but otherwise, like unlike electrostatic theory, this EAN rule is very successful. Okay, electronic atomic number or 18 electron rule is very successful, and this has very good application in organometallic chemistry, right? So it's done. Today's discussion is done. So in the next session we will be talking about PBT. That is very important for your exam perspective and for your knowledge, of course. That is important, of course. So we'll meet in the next video. Till then, bye bye.